welcome everyone, and thank you for attending. We have a very large audience, and I appreciate everyone attending early in the morning. Also, I'd like to say thank you to Tropic Supply for actually organizing this and getting such a large number of attendees to join us in this seminar. As Nicole indicated, this is the first 6 items here are really fundamentals of air conditioning. It's really a basic AC class on the components of air conditioning and talking about superheat, subcooling, a lot of definitions. The last three um, or the last two are really getting into the technology that we're using with digital gauges now and digital tools, and why there's a big trend in going to these tools today. Just to give you a review of Testo, everybody hopefully knows Testo, a very large company. We're German/US company, over 60 years of development experience. All we do is manufacture instruments, digital gauges, and you'll see a list of instruments on there. Maybe hopefully some of you are using those instruments already. One thing to bring up here is that we are ISO 17025 quality standards, and ISO is an international standard where we, in our New Jersey headquarters, we have the calibration equipment and the protocol to maintain very accurate measurements on our tools. Every tool that we send out is calibrated to certain specifications, and we're going to be talking a lot about accuracy today, accuracy of digital gauges. I wanted to bring this up to you. Like I said, we're based in Sparta, New Jersey. I'm out of North Carolina. I'm in the southeast region of the United States, and perhaps some of you have heard my presentations before, or maybe I visited with you in some occasion. One thing too, that not only do you have Testo support, we have a very good rep organization in Florida. Hopefully most of you know Jay Nichols and Associates. They're our local support. Joanne, Whit, Nick, and Jim are quite in the field a lot with the Testo instruments, working with Tropic Supply at open houses and counter days and things of that nature. And obviously you can go to them for questions and answers. Also, you can go to Testo, and also you can go to Tropic Supply. We sell our products through Tropic Supply in Florida. So let's get into the presentation a little bit, and what question everyone has is why we going from analog gauges to digital gauges. And really it's what I consider 4 different things that's taken place is the systems are changing, AC systems are changing. We're getting involved more with different refrigerants. You'll see a lot more in the next year, I'm sure. Higher SEER ratings, things of that nature. But it's all about customer value, and we're trying to install and service these air conditioning systems, refrigeration systems to the OEM recommendations so we can get peak operating performance. Professionalism, certainly everyone on this in this seminar is a professional. You know a little bit, hopefully a lot more than you think on AC, the operation of an AC system. We're considered professionals. You're considered an expert in the industry, and again, we want to complete the job efficiently and correctly the first time, trying to reduce our callbacks. Safety, we're meeting local regulations, OEM recommendations on safe operation of equipment, and profitability. We're all on here to make money, and we want to do the job right the first time in an efficient manner so we don't get the repeated callbacks. So if we get into the laws of refrigeration, some heat transfer laws, couple questions here or couple theories is that heat always moves from a higher temperature to a lower temperature. I think most of us obviously know that. We have heat, and heat always moves from more heat to less heat. absolute zero temperature. Maybe a few of you on the line, or maybe many of you know what the absolute zero temperature is. And that's a term that we use. It actually goes down to minus 460 degrees Fahrenheit, where we have no heat. That means that we have no the molecules quit moving at minus 460 degrees. Everything above that, when you get into minus 300, minus 200, 0, 32 degrees Fahrenheit, has heat. We call it cold, but it's less heat or more heat. If you get down to minus 460, which I don't think we can do on Earth anyway, you would have zero heat. Gas pressure laws. There's a lot of gas pressure laws out there, but the laws, the key one that we need to know is that pressure and temperature are directly proportional to each other. That means as we increase the pressure in the system, the temperature will rise. If we decrease pressure, we decrease temperature, and that's where the compressor and the metering device takes place. Fluids absorb heat while changing from a liquid to a vapor. We know that's in the evaporator, and fluids give up heat while changing from a vapor to a liquid, and that's in a condensing unit. So another definition here before we get into some of the basic theories again is BTU. Everyone sure has heard the term BTU. They know what it's about, but this is just a review. BTU is the amount of heat necessary to raise the temperature of around 1 pound of water, 1 degree Fahrenheit. So we talk about BTU, we're really talking about energy to raise the boiling point of, or the temperature of water. So on this screen here, we have on the top, you'll see three, uh, three states of matter, solid, liquid, and vapor or steam. And what this bottom chart represents is the change. And I use water. Water is very visual. We all know that water boils at 212 degrees at sea level. I assume that most places in Florida are at the sea level. But as we add heat energy, as we add BTU to water, you can see the transition of water from left to right going through the different states of matter. Excuse me. So it starts with ice, a solid, goes from a water vapor, goes from a liquid to a vapor. Same thing happens with refrigerant. Although we don't have a solid in refrigerant, we do have liquid and vapor. And if you look at um, as we add more and more heat energy or BTU to something, as we add pressure to a system, we're increasing the temperature. So you'll see that with water is the temperature will rise at 32 degrees. It's a liquid, and it's going to increase as we increase temperature. As we increase pressure, we're going to increase the temperature of water till we reach a point where we call it saturation, where we have a change of state. And as we change at 212 degrees and at sea level, which is 14.7 psi, the water temperature does not rise in temperature. What happens is that we have a change of state. We're going from a liquid to a vapor, and that's where you get this straight line right here. Until we reach a point where we transition to all vapor. And when we transition to all vapor, then we start heating up the vapor. And this is where you see the line here above 212 degrees. So here, what you see here on the top right is called superheat. And if you go to when we're heating water or heating a refrigerant, this is where we have what we call vapor, or I'm sorry, liquid. And that's where we have subcooling. Like I said, water is very visible. So we know where the boiling point of water is at 212 degrees. When you're dealing with R22, they have an R410A, for instance, or for example, they have much, much lower boiling points. For instance, R22 boils at minus 441 degrees Fahrenheit. 410A boils at around minus 61 degrees Fahrenheit. So, so here with this line here, the level line here is where we have what we call saturation. We have a change of state, and that occurs in our coils. If we go to the reverse and we reduce the heat, then we're changing from a vapor to a liquid And what's causing this change is the components in an air conditioning system. We have four major components in an air conditioning system. And the compressor is the pressure increaser or the pressure inducer. That's causing the vapor. That's creating a pressure change from a low pressure vapor to a high pressure vapor. The condenser is a heat rejector. Talking about these, so the condenser rejects the heat from the system and changes in the condenser unit. We have high pressure vapor, and we're going from a high pressure vapor to a high pressure liquid. In the metering devices, the second part of the pressure change is a pressure dropper, which is a metering device before it gets into the evaporator. Again, we're changing the pressure of the refrigerant from a high temperature, high pressure liquid to a low temperature, low pressure liquid. Then the evaporator is what we consider the heat absorber. That's absorbing the heat from the refrigerant. And again, we have another change of state in our evaporator coil. We go from a liquid to a vapor. And then the refrigerant itself is the heat mover. That's moving the heat from a place where we don't need it, which is outside, to a place where we're moving the heat from a place where we don't want it, which is inside the evaporator, the building, the home, and moving it to outside where we can release the heat. So if you're looking at the complete cycle with all the different components, remember that again, we're going from hot to cold. So we want to follow the heat. And as we start, let's just start at the compressor. Oops, sorry about that. But if we start at the compressor, the refrigerant vapor is compressed in the compressor and now moves to the condenser. The refrigerant is at a high temperature, high pressure vapor. Since there is more heat in the refrigerant and less heat in the outside air going through the condensing unit, the condenser coils are transferring the heat from the refrigerant to the outside. And as this refrigerant rejects the heat in the condenser, the refrigerant condenses and becomes a liquid. So you're going from a vapor to a liquid. At the condenser outlet, the refrigerant is now at a high pressure liquid. High pressure liquid refrigerant travels to the metering device. Here we have a TXV, and as it enters the TXV, the metering device again is reducing the pressure, therefore dropping the temperature of the refrigerant as it travels to the evaporator. And as it goes into the evaporator, now refrigerant has less heat, and as it enters the evaporator. So now in the evaporator, now there is more heat in the room air passing over the evaporator coil, and the heat is again being transferred to the refrigerant now from the distribution air, causing the refrigerant to boil from a liquid to a vapor. Evaporator is transferring the heat from the room to the air, and so we feel comfortable. At the outlet of the evaporator, the refrigerant is now at a low temperature, low pressure vapor as it travels again to the inlet of the compressor. Complete cycle. It's been the physics behind this is been around for a long time. I think the physics behind this developed back in the early 1900s, and mainly the physics and the science behind this still remains the same. It's kind of, for me, it's kind of a remarkable cycle that can last a long time, as long as you maintain the the equipment properly. So one thing that we need to know a little bit as contractors and service technicians is we do need to know a little bit about the science and the physics behind air conditioning units. And this goes back to the term in the beginning we call professional. We all need to know a little bit about the cycle, the refrigeration cycle. We need to know about the pressure temperature differences. We need to know a little bit about physics and science to understand this refrigeration cycle. And as you know, this refrigeration cycle is most of your customers, unless you're dealing in the commercial market, but most of the homeowners, residential customers don't really can't grasp this cycle as much as you can because they're not studying it every day as you are. But again, pressures and temperature measurements are very important. As I said in the beginning, it's very critical now because we have less forgiving refrigerants. We're going to have a lot of new refrigerants coming in 2022, I believe, higher SEER, higher capacity ratings on our equipment, leading to a change in our tools than the traditional tools that we've been using. And when we change from traditional tools to the digital tools, it's really all about the accuracy on the measurements that we're taking. So again, we're looking at changes in the equipment. We're going to be talking about superheat, subcooling. We're going to talk a little bit about how do we do it in the past? How do we do it using a digital gauge? But here's just a quick illustration of where the service ports are and where we're taking our primary measurements to get superheat and subcooling. One thing too, before we get into the AC side too, is another measurement that we need to do, which is overlooked, is airflow. Airflow, actually, before we do any type of charge or maintenance on the system, airflow has to be measured. Typically, it's one of the first things that are measured, and we're setting the airflow over the coils and setting it to a nominal 400 CFM per ton on AC equipment, maybe 450 CFM per ton on heat pumps. That may change a little bit because of the conditions in Florida, and that's why you want to refer to the manufacturer's specifications on the amount of airflow for their equipment. And there's ways of looking at airflow. You've seen these instruments before, I'm sure, but the propeller type instrument is a vane anemometer. It measures feet per minute. There's differential pressure for static pressure test. There's duct thermal anemometers that go inside a hard duct to traverse the ducts. And there's also flow hoods that are used a lot in the commercial market for test and balancing. One thing to know is when we're doing airflow test, typically we're measuring the feet per minute, and feet per minute is the speed or the velocity of air. We still need to look at the area of the duct size to get the cubic feet per minute or CFM. And that's a volume measurement. CFM is a volume measurement. So we need to know the dimensions of the ducts itself so that we can get the correct area, and we can calculate the CFM from the feet per minute that we're measuring. Another measurement, and this goes back to air conditioning again, is a dry bulb rating. Obviously, dry bulb is ambient air temperature. When we measure, we use different types of probes, K-thermocouples and NTC probes, which I'll get in a little bit later, to measure temperature. Relative humidity is a key component in servicing our equipment. Amount of water vapor in the air. We used to use what's called sling psychrometers. But today we're using digital gauges and digital relative humidity instruments. And these relative humidity instruments are extremely accurate. I talk about accuracy a lot in this presentation. When I say plus or minus 2%, I mean plus or minus 2. That means that if you're reading 70% percent relative humidity, plus or minus 2 is between 68 and 72. And that's the tolerance of the instrument. It should be within that plus or minus 2 tolerance or range. We'll talk a little bit about targeted superheat, load capacity test, comparison readings, ambient comfort. That's, oh, excuse me. So if we get into wet bulb, most of you are familiar with the term wet bulb. And in the past, we use a wet bulb, which is a thermometer with a wick on it. And we used to moisten that wick with distilled water. We'd do a comparison of a dry bulb and a wet bulb by spinning they call a sling psychrometer. And the difference between the wet bulb reading and the dry bulb reading would provide us the relative humidity. Today, again, another way of looking at wet bulb is when you get out of the shower and your skin cools down. That's a result of, that's your wet bulb temperature reading. As your water evaporates from your body, it's creating a lower temperature, and that is considered the wet bulb reading. Again, sling psychrometers, probably no one is using any sling psychrometers anymore. They were back in the 60s and 70s, back in my time, if I go back many years ago. But today we're using temperature measurement instruments. Most relative humidity sensors today have temperature sensor as a specific relative humidity sensor. And we're using, we're, we're using the wet bulb reading. We're calculating it from a sling psychrometer chart. Obviously, digital gauges have chips in them, and they're doing the calculations for you automatically. Very important measurement is the temperature reading, the relative humidity reading, and the wet bulb reading. You can see what you can do with just having, and again, this temperature relative humidity instrument, we call it a 605i, but it's a digital, I call it a digital sling psychrometer, and it has no display. You're using your smart device to get the readings, and we'll go through that a little bit later when we start talking about the tools. But these have a distance of around 300 feet, 350 feet away from the cell phone itself, and you can set them up in different areas of the room and get your readings, your relative humidity, temperature, and wet bulb readings throughout the room. You can hook up 7 or 8 of these probes to one cell phone, depending on the type of cell phone you have. So a very common instrument we're using today is the digital relative humidity instruments. Again, very popular, very affordable. We're not talking a lot of money for an instrument like this. Looking at a good one costing about 125 bucks with a 3-year warranty or so. These instruments last quite a long time. Talking about a little bit about pressures, going back to pressures, as that previous slide we went through, when we add heat, we change from a liquid to a vapor. When we remove heat, we change from a vapor to a liquid. And we call that in a sealed system, and that's what we have in an air conditioning system, is consider the term saturation. And saturation is obviously when you add heat, you'll see on the far right beaker there that the liquid is changing from a vapor and then from a vapor to a liquid. Nothing is being lost in the process as far as the refrigerant. Evaporation, we all heard the term evaporation before. We boil water at 212 degrees. We evaporate, the water evaporates in the air. We lose the water molecules. Obviously, that's considered evaporation. So if we have a leak in a refrigeration system, then we're going to be losing, obviously, the refrigerant molecules, and therefore it's not going to have the correct cooling capacity as specified. So what is superheat, subcooling, and saturation? You know, superheat, as we showed on the graph previously, superheat is the temperature of the vapor above the saturation temperature. The subcooling is the temperature of a liquid before it be below the saturation temperature. And then the saturation point is, again, where we can either add add heat or lose heat without changing state. Uh, and that's where we have a temperature that does not change as we're changing state. And an easy way for me to remember this, obviously, is that superheat has no liquid present. So you would be up at that far right part of that graph there. There's no liquid present. It's all vapor. Subcooling, on the other hand, has all liquid and no vapor, and both. And the saturation is the horizontal line where the water is boiling, and both liquid and vapor are present through the process of changing state. And as we add heat, we're adding heat by changing pressure. We're reducing heat by reducing pressure. So why are we measuring superheat and subcooling? Well, compressors are only designed, as we all know, to pump vapor. Superheat ensures that no liquid enters the compressor, and the metering device must have a column of liquid to operate properly. And subcooling ensures uh, that a solid column of liquid enters the metering device. In a lot of cases, you may be dealing with fixed capillary or piston type metering devices. Most systems today are TXV, but superheat verifies evaporator performance. Subcooling ensures adequate refrigerant is going to the metering device. Checking superheat. When do we check superheat? Anytime we break into the system. We have a compressor failure, TXV replaced, when the system is not charging or not cooling properly. And anytime we change refrigerant is changed or added to the system, again, we need to check superheat and subcooling. The analog method that we've been using since the beginning of time, again, this technology goes back to early 1900s. The analog gauges that we use to get the pressures. Um, we're using a temperature measurement. We're using hopefully an accurate surface probe thermometer, and we're doing the math by converting the pressure to the saturation temperatures using a PT chart. An example of this is, say, 410A is a refrigerant. So on the low side, your operating vapor pressure would be, say, 140 psi-G. And psi-G is gauge pressure. That is not the ambient air pressure. At psi-A is what we call absolute pressure. That would be the atmospheric pressure plus the pressure in the system. When we do psi-G, we mean that we're zeroing the pressure sensor. In most cases in Florida, we're zeroing the 14.7 psi at sea level to zero. And that's what they mean by psi gauge pressure. 140 degrees, 140 psi-G. We use our pressure temperature conversion charts. We can get, we see the difference of 49 degrees Fahrenheit is the saturation temperature. And we still have to use a temperature sensor to get the vapor line temperature. And we do a little bit of math. We get to 63 minus 49 equals the 14 degree superheat. Today, we're transitioning very quickly to ways of getting away from the analog gauges. And there's different ways of getting, there's a whole variety of digital instruments that we have that you can get into using digital gauges from using what we call smart probes, independent probes with no hoses that go directly on the service ports, or we can use hoses with the digital gauges and also get the superheat and subcooling. So again, we're hooking the gauge up to the same to the low suction line side. We're looking at blue hose to the blue side, red hose to the high side. We're throttling the refrigerant into the system and seeing instantaneously, not instantaneously, but over as we add a charge to the system, it has to equalize through the entire system, and you'll see the results on a digital instrument. No need to use pressure temperature charts anymore. Again, low side suction line temperature. We're using what we call wireless probes now. You don't have to worry about plug-in type temperature probes. These are, again, in this case, it's on the suction line, and we're getting the temperature of the suction line through a wireless temperature probe. You can see here the service ports and where we would take the temperature measurement. Again, you're not using any type of math. All the calculations are done through a chip. Just put in the correct refrigerant, and there's over 90 different refrigerants in these instruments. So as you're charging the system, you're looking at superheat. It's doing the math for you based on the refrigerant that you select, the temperature measurement on your suction line, and the pressure that's on the suction line itself. Very quick, very fast. So when you get your superheat, whether you're using an analog or digital gauge, you still need to have a targeted superheat. And in thermal expansion valves, have a fixed superheat roughly between 8 to 12 degrees Fahrenheit. Some OEMs are usually slightly lower, but check with the manufacturer. Sometimes if we don't have the TXV and we got a piston type, we got to figure out our targeted superheat. When we figure out our targeted superheat, we got to, again, know the indoor wet bulb temperature and the outdoor dry bulb temperature. In the past, we used to use formulas. We used to use charging charts. Today, again, it's back to this digital relative humidity temperature instrument where we are taking the outdoor temperature, dry bulb temperature. We're taking the return air wet bulb temperature inside the room, and we're getting the calculated targeted superheat. It's done very quickly on these instruments, and you're matching the actual superheat to the targeted superheat by using additional what we can call smart probes, 605i smart probes. Or you can just insert the outdoor dry bulb manually and the return air wet bulb manually as well. And again, if the actual superheat is too high, we need to add refrigerant. If the actual superheat is too low, we need to remove the refrigerant. On these digital gauges too, you'll see that this would be a display. Very far right is your display for looking at superheat, subcooling, and your targeted superheat all together on one display. Unfortunately, this is in metrics. This is a slide that I received from Germany. I didn't convert it to degrees Fahrenheit, but everything would be PSI and degrees Fahrenheit. Subcooling, again, again, we must have a solid column of liquid entering the orifice. And again, we're using PT chart. We're on the high side of the system. We're using we're using a gauge, high pressure gauge, accurate surface thermometer, and we're looking at 432 as a PSIG, which is measured. We take that, look at a PT chart that corresponds to 122 degrees Fahrenheit, and we look at our liquid line temperature, taking a measurement of that at 110, and we subtract the saturation temperature from the line temperature, which is 122 minus 110 to get 12 degrees Fahrenheit. Again, we're back to digital gauges today. Again, a full line of instruments, whether you're starting at $100 to all the way up to $600-700, depending on the type of instrument or configuration you're looking at. But again, we're on the high side of the system. We're using wireless probes, and we have two of them here, one on the low side, one on the high side. So we're taking both the superheat and subcooling uh, calculations. We're taking those into account by with one instrument, not going back and forth and doing your measurements. And again, subcooling is a saturated temperature minus the measured temperature. And and again, subcooling is design number from the manufacturer. That's usually on the nameplate or the instruction manual. So you got two sides that you're looking at. You got the low side, high side, subcooling high side, superheat low side. And again, here's some interesting things about the superheat and subcooling. Most of you, I'm sure, know this already, but it's just again a repeat of what we talked about. Superheat's too high, then there's not enough refrigerant being fed, resulting in poor refrigeration, excess energy. Superheat is too low. You can see what happens there. Subcooling is too high and subcooling is too low. Just some general conditions on what to do when you're getting the readings that are not within the specifications of the equipment. So that's another reason why our tools are changing, because the specifications of the equipment are getting more and more tighter. And one thing, as we get into just the instrument side of this, um, everyone probably has an infrared thermometer, and infrared thermometers are a great tool for looking at primarily only surface temperature. We don't, if you point a infrared thermometer at a supply duct or return, you're not getting the air temperature. You're getting the temperature, the surface temperature of the grill itself. So keep that in mind. And these are not to be used on refrigeration lines. What we're using today are pipe clamp probes, obviously. And the pipe clamp probes, there's two different types of sensors that we use. Testo uses what we call NTC, which is a temperature resistant type uh, um, sensor, and a thermocouple, which is a thermocouple is two dissimilar metals that are joined together, where we measure the voltage change. And then NTC is what we call negative temperature coefficient. So it's a technical term for as the temperature goes up, the resistance goes down. And the important thing to remember here is that NTC goes up to 302 degrees, whereas TC thermocouples can go up to 2,500 degrees. And typically in a air conditioning refrigeration application, NTC, we're at very low temperatures. So the NTC sensor is used a lot in low temperature applications, whereas the type K probe is used a lot in heating applications or just general temperature measurement. But the real accuracy is at the lower range where the NTC probe is. So the thing about thermocouples is thermocouples do drift over time. They do need to be calibrated. And I'm not so sure a lot of us are calibrating our thermocouples in the field. They typically need to be calibrated once a year. That's tough thing to do when you're in the field. But with NTC, just keep in mind that NTC has a very good operating range for temperature measurement in refrigeration systems. Its accuracy is much better than the thermocouples. And the big thing really is that there's no calibration. And most of you that are using a Testo, whether it's a plug-in probe or a wireless probe, you know that when you turn those two probes on in ambient temperature, you're going to get roughly the same reading. What I mean by roughly the same reading, it's going to be plus or minus 1 degree difference, and even less than that. It's remarkable how stable these NTC probes are. And just like anything else when we're measuring temperature, there's an element in that pipe clamp probe. This happens to be a thermal image picture of a suction line and a pipe clamp probe that's on the suction line. And you'll notice the different colors. And the thermal image, we manufacture thermal cameras as well, but we're looking at the difference in colors gives us a difference in temperature. These are extremely accurate measuring devices. The military uses thermal imaging quite a bit, law enforcement, of course, but we're also seeing a lot of thermal imaging now because it's now affordable in the HVAC market. But back to the sensor is that yellow or that blue um, sensor that's in the jaw of the pipe clamp, and it's touching the suction line. The and that suction line color, dark blue, is the same color as the color of the sensor in the pipe clamp probe. And what that's doing is that's transferring that measurement into the instrument. So we're really measuring the sensor, the temperature sensor itself, rather than the pipe. There's a transfer of heat again from the suction line to the element or the NTC sensor in that pipe clamp probe. But again, today we have a lot of questions about maybe some customer dissatisfaction, callbacks, system failures, things of that nature. And as we know, these are what we've been using in the past, and I believe a lot of you are converting to digital gauges. One of the things that we've been asking ourselves, and maybe you've been asking yourselves, is, am I using the correct instruments? Uh, some instruments may be substandard, instruments are out of calibration. We all have different procedures in doing these calculations, and maybe we're using the wrong tool. What's happening and what's changing is that everyone in the past had a really inconsistent method of checking superheat and subcooling. What digital gauges has allowed us to do, and not only that, but the accuracies are much greater on digital instruments because of these reasons. Much greater on analog. Again, you have temperature differences, and you have some gauge inaccuracies, calibration errors, things of that nature. And these are just some of the calibration errors primarily that you're looking at on the pressure side of these analog gauges. Even our temperature charts are outdated a little bit, not so much outdated as much as they become inaccurate at certain sections of the temperature pressure chart. And we're all have questions about digital gauges. Over the past, some of you have been using digital gauges. Others are probably just finding out the benefits of these gauges. But really what digital gauges provides us is it's a higher accuracy. Hopefully it's going to reduce your callbacks. That's what it's all about, is getting the measurements up front correctly, accurately, and reducing your callbacks. You can do a lot of complex functions. You can do trending charts, data logging on these instruments. All the calculations are done automatically. Like I said, they stay in calibration. There's no way the temperature sensors do not need to be calibrated. Pressure sensors can be zeroed at any time in the atmospheric pressure, but just hitting a button, a key on the display on the panel itself. The nice thing too about these is their excellent repeatability. If you have a technician that has two weeks experience in the field, all he needs to do is hook up the blue hose to the blue side, the red hose to the red side, put on the pipe clamp probes, one on the suction, one on the liquid, and the instrument is going to automatically calculate everything for him. He's going to get the same readings as he would as an experienced contractor that has 20, 25 years experience, because it's the instrument's doing everything, the work for you. All the operator has to do, the service technician has to make sure that the probes are hooked up correctly at the right locations. Again, these are extremely accurate instruments. Again, ISO certified. They're calibrated. They're very durable. There's a lot of ways of using these digital gauges, charging, troubleshooting, targeted superheat. We went through a few of these already. Superheat subcooling, where you're using the instrument and you're transferring the temperatures. The temperature pipe clamp probes are now wireless probes that communicate directly into the instrument. If you're not using the instrument, you shut the instrument off. These two pipe clamp probes will go directly into your app. So the way this thing works is that it takes up to 4 probes. All of them are wireless, including the vacuum sensor. The vacuum sensor is now a wireless sensor that communicates to the instrument, and that happens to be what we call a 557 4-valve. It's communicate all these wireless probes are communicating to the instrument. From the instrument, it's going into your app. If you shut your instrument off, which is at 557, those instruments will then be redirected to the app. So you can use these with an app, or you can use them with the instrument through the that eventually communicates to the app. A lot of versatility in these instruments. This is the wireless probe. We've designed a wireless probe so it's separate from the instrument. And this allows for better accuracy because you're closer to the system. You're teed into the vacuum pump, but you're closer to the system, and there's no chance of leaks as you go through if you have a vacuum sensor that's internal in your instruments. Typically, when you pull a vacuum through an instrument, you could create leaks in your connections, your valve stems, even your hoses. This allows us to go directly closer to the system, and it communicates either to the app first or to the digital gauge, whatever method you want to use. Digital gauges, again, they do a lot of different measurements, and this here happens to be the menu of a 550 550S, we call it. But you'll see not only are you getting numbers, but you're also getting a graphic representation of what you're looking at. So if you're looking at targeted superheat at the far right there, you'll see the gauges, simulating gauges. You'll see the numbers which represent the PSI in the system. You look at the evacuation screen, not only are you getting the micron measurement, but you're also getting a graph that shows the trending of microns when you're doing a vacuum. So you can set the target pull down at 500 microns. You can set the decay rate at 800 microns, and the instrument will alarm you. The cell phone will alarm you when you exceed those parameters. Pressure leak test is a positive pressure leak test using nitrogen. Again, very accurate method of doing a nitrogen test on your system. Differential pressure. A compressor test is using three wireless probes, one on the discharge line of the compressor. Again, it's all about the accuracy, guys. Plus or minus 1 degree Fahrenheit on thermistors. NTC probes require have an accuracy of plus or minus 1 degree Fahrenheit. Thermocouples are a little bit higher. Plus, thermocouples need to be calibrated periodically. Accuracy of pressure sensors plus or minus 0.5 psi instead of 3-4 psi. Then it comes down to looking at better tools, hopefully better job, better customer satisfaction, higher satisfaction, more recommendation, more jobs, and more money, more profit for you. And really, that's one reason why we're here. And obviously, if you for yourself or for your company, if you're making more money, you got some better tools, toys, you got more vacations, maybe a happier spouse or the happiest spouse, whatever. So yeah, it's all about reducing callbacks and doing the job right the first time. Other things you can look at on digital gauges together is looking at the pressures, head pressure, suction pressure, superheat, subcooling. If you're doing amp draws, you can look at doing a system analysis and looking at some of the symptoms that you have that you can diagnose a lot quicker. Just a quick review of Testo. This really terminates the NATE program. I just want to give you a quick update on Testo. A lot of different ways of checking superheat, subcooling, different configurations of instruments. Everything with us is wireless now, like I said, including the vacuum sensor. And again, the vacuum sensor is wireless because it provides better accuracy. It's less chance of having leaks when you pull through the instrument. It's a very reliable vacuum micron gauge. Again, you're going from the digital smart probes to the instruments and then to the free Testo app. So you really have, if you're using a 550, 557 digital gauge with a display, you got two displays, a remote display and you got the local display, which is on the instrument, providing graphics on both the app as well as the instrument. Just to give you some ballpark pricing, again, these are Testo's list pricing. Go to Tropic Supply for pricing, but you can see that these are, I consider them affordable. The two valves are on top, two valve, they all come in hard carrying case, certificate of calibration. They come with a 2-year warranty. That is standard. You can get an extra year warranty if you register the serial number of the instrument on our internet site, and you can get an extra year warranty, which brings it up to 3 years. The four valve structure, four valves automatically come with the vacuum sensor you'll see there. Again, hard carrying case. These do come with and without hoses, depending on what configuration you want. Again, key features starting at around $500. Again, the key here is that the apps are free, 2-year warranty plus extra 1-year warranty on registration. Very durable. It's here is your 4 valve, which we call a 557. Again, there's a starting price there. Some of the features of the instrument. Micron sensor again communicates. It's a separate sensor. Communicates first to the digital gauges and then to the app, or you can strictly go into the app if you're not using digital gauges. The other thing here is it's very common in the industry now is Bluetooth. Bluetooth has come a long way over the last 4 or 5 years, and we have a full lineup of what we call Bluetooth. We call these smart probes. And you can see we start at airflow, with differential manometer, pressure, pipe clamp probes, relative humidity. Some of these you've seen in the previous slides. We keep adding to these. These probes start at around $80 and can go up to $120 individually. You start looking at kits. This is a Superheat subcooling kit where you got 2 probes, pressure probes, one on a suction, one on a liquid, and we have 2 pipe clamp probes, one on the liquid, one on the suction line, and we're calculating superheat subcooling through the app itself. So there's no display, remote display other than your smart device. Different methods, different ways of looking at this. The app allows us to do a lot of different things. Once it's in the app and your smart device, you can store the readings under a customer name, under a site location. You can do a lot of different graphics. You can see there, and it's really a free app from Testo. The app is it's a new app. It's called a Testo Smart App, and the app can be used by itself. One app for the smart probes as well as the digital gauges. Now that really concludes my part of the presentation on the NATE side of things. Nicole, you still there?
Yeah, we're both still here.
I am.
Yep.
Okay. And as I indicated to you, this is a NATE class. And you could you could send your NATE information to my email, jfigan@testo.com. All I need is your name, your first and last name, and your NATE ID number. I do believe it's a 7-digit number. and I will handle it through the NATE website and get you a credit on this class.
Okay, I think we should
And
turn
I'll
it
be
over.
including that information. Yeah, real quick, I'll be including that information in the follow-up email that you guys will get after today's class. So you'll have that information available to you.
And I was just gonna say, Todd, is there any questions in the chat box? If you guys have any questions for John, please put them in there. But Todd, can you take a look back at what people have put in there to see if we have questions?
Yeah, so far, no, we haven't really had any questions.
We'll give you guys a few minutes to type it in. Now's the time. You got the expert on the phone. And then we'll move on to trivia questions and prizes. All right, I don't see anything. Nicole, you want to move over to trivia questions?
Yes. We will do that right now.
Okay, well, wait, now we got a question, couple of questions popping in.
That's okay.
Hey, Todd, how are
They're
you?
asking, is the subcool and superheat, is that the temperature at the center of the coil? John, you still with us?
Oh, I'm sorry, I got disconnected. Superheat and subcooling, yes, it's at the center of the coil.
And are the probes rainproof?
The probes are, we can't really call them rainproof because someone would throw them in the water in the ocean down there, but they are what we consider waterproof. Both the digital gauges and the smart probes are we can't call them waterproof, we call them rainproof. You can go on internet site. People are checking these out already by throwing them in water and spraying water on them. They are IP54, which means that they're rainproof. They're sealed. We seal these instruments very, very well with gaskets and O-rings and things of that nature. The digital gauges are I could say they're really rainproof, but you really can't throw them in a bucket of water. The smart probes, I wouldn't throw them in a bucket of water, but they certainly are resistant with water on heavy rains.
Do the new probes, are they backwards compatible to the older manifolds like the 550?
No, they are not. The 550, the old 550s used wired probes, and the wireless probes do not communicate to that older 550.
Okay, are they battery operated or rechargeable batteries?
Yes, they're battery operated. They're off the shelf 4 AA batteries. Nice thing about with these digital gauges is the batteries last a long time. The only thing that consumes the battery is the backlight itself. That shuts off automatically, but you can get hundreds of hours of operation with a set of 4 AA batteries.
Yeah, I can tell you that I have a set of these probes. I love them, use them often. Definitely not as much as you guys in the field probably use them, but I'm going on probably a little over a year now and haven't had to change the batteries yet. So they
good.
definitely get a long battery life. Let's see, there's something about refrigerants. Bear with me here. Will the superheat and subcool readings change with the new refrigerants?
Yes. Anytime you change refrigerants, whether it's a new refrigerant or with the old refrigerant, if you go from 410A to R22, obviously it's going to provide a different superheat subcooling. One thing that I did not mention on the app is that the app allows us, the Bluetooth allows us to update our instruments when we make a change in the app. And we've done this already once already since we introduced the new app in February of this year. Anytime a new refrigerant is available, let's say what's the new one? Is it 454? In fact, I think there's one coming out that's already on our new app. So the the app allows us to keep the instrument, the 550 or the 557, updated with all the current new refrigerants. And you simply do that by deleting the old app and uploading the new app. And the new app will carry, not only will it carry the new refrigerants, but it may carry a firmware change that we use, well, that we upgraded the instrument somehow with a new operating sequence or something that, a new calculation that you guys are using in the field, things of that nature. So it's very fluid. When you purchase and you're going to have these instruments a long time. Like I said, Testo has a up to 3-year warranty. But as Todd indicated, you can keep these instruments 5, 6, 7 years in the field, and you'll have very little cost of ownership on these instruments. They last a very long time, and if you're going to keep them for 5, 6, 7 years, you got to keep them updated with the new refrigerants, and that's easily done through the app and the Bluetooth capability.
How can you tell when there's a contaminant in the system?
You can't tell if there's a contaminant in the system through the digital gauges.
Now, I would tell you your first clue is going to be chances are your temperature and pressure is going to be way off from what
Okay.
you're typically reading. And it depends on what that contaminant is, whether it's a non-condensable or not. Are instructions on how to use Bluetooth instruments available online?
They're online as well as the app. If you download the app, and you can do that right now if you want, it's called Testo Smart, and there's a tutorial in the app under information. So you can run through a quick tutorial on how to use the app when you download the new app.
There's also a lot of great instructional guides and videos on their website. There's a know-how section on the website that'll lead you to that at testo.com. Let's see what else we got. Are these compatible with the new more flammability refrigerants coming out? Yeah, we already talked about that.
Yeah, and one thing I want to mention too, and maybe a question everyone has, is can you go from R22 to 410A or changing the oil? Will that result in contamination of the sensors? And the answer is no. It's prefer that you flush the instrument out. You're not going to contaminate, you're not going to damage the instrument. But what refrigerant suppliers have told us is that they like to either use separate hoses or flush out the manifold itself with a nitrogen or so. You don't want to cross-contaminate this air conditioning system. You won't damage the instrument regardless of what you do, but you don't want to cross-contaminate.
We have a contractor that's got one of the older digital gauges that had the wired temperature probes, the wired clamps.
Yes.
Those aren't Bluetooth, are they?
They are not.
I didn't think
No,
so.
the wired probes are not Bluetooth. Again, the older instrument goes back about 10 years ago, and at that time we didn't have Bluetooth capability. So yeah, you have to. Unfortunately, if you want Bluetooth, you got to buy either a smart probe kit or you got to buy a digital gauge, a new. We call them 550S. S being whatever you want to say, smart, whatever. But yeah, you gotta buy the new gauge to upgrade to the digital probes.
Got a couple questions on the new refrigerant. I'll touch on that a little bit, but that's really a whole different topic of conversation. Basically, for those of you that are not aware, and hopefully you are by now, but there's an expected refrigerant change coming January 1st of 2025. That is most of your residential equipment manufacturers, your conventional equipment manufacturers, if you will, your Rude, your Allied, Samsung, or those are all, they're going to be switching to either R454B or R32. Typically, we're looking at the R454B in most of your conventional style equipment and the R32 in your mini split style equipment. You'll also be January 1st, 2025, there'll be no longer disposable refrigerant cylinders. Everything will be on an exchange basis type cylinder, similar to what you're doing now with your oxygen acetylene. We had a class on that earlier. We'll probably be doing more of those as we get closer to 2025, of course. But again, those don't take effect until January of 2025.
Hey, Todd, I want to just pipe in and say that if they're interested in getting a recording of that refrigerant seminar that we did with Wade Hadaway at Rude, they can just email nicole.parrish@tropicsupply.com and she'll send the link.
Okay.
Or we can also add it to the email that we're going to send out after the meeting with the other recording.
And we touched
can
on
do
this,
that.
we'll touch on it again, but basically no, the older 550s are not Bluetooth compatible. Some of the newer ones are, but you would need now the older probes are Bluetooth. So some of you may have the earlier set of probes that didn't have the angle pressure port on it, or didn't have the flexible bend on the hygrometers. Those are Bluetooth compatible. Now, John, do those work with the new app, the older probes, the first edition probes?
Yes.
Okay.
And that's a good point. We, the old app, which was called, I think it was called our Smart Probe app, is no longer available. You have to upload the new Testo Smart app, and and you can use the old smart probes and the new smart probes and the new digital gauges with that Smart Probe app.
Okay, great. That's about it. Nicole, looks like everybody would like a link to that refrigerant seminar that we
Yeah,
did.
that's no problem. I have a note to add it.
Okay. All right. I think we can go ahead and jump to the
Quiz questions. All right, guys, everybody get their typing fingers ready in the chat box. First one to answer the first question correctly, I'm going to call as the winner and you'll get that super duper fabulous flashlight.
Okay, here we go. Question 1, in air conditioning systems, where does the refrigerant give up heat while changing from vapor to liquid? Okay. Question number 2, which AC component creates the pressure drop in the system? All right, question number 3. What is the one major benefit of going from analog tools to digital tools? Okay, question number 4. Why has Testo developed a Bluetooth smart probe to measure microns?
All right, everybody. We will talk to you soon.
Thanks everyone.
Thanks,
Appreciate the time.
everyone.